Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing well. My name is Azmat Ali and I welcome you all in class of Real Analysis, Principles of Mathematical Analysis by Walter Rudin. In today's lecture, we will discuss Archimedean property of R. Before going to start its statement and proof, I want to give what is the idea behind the property. So whenever we discuss or we take any two real numbers, suppose I take two real number x and y, and now there are two possibilities: either they are equal or they are not equal. Suppose they are not equal and y is bigger than x. No matter how large y is, I can find always an integer n. This is a positive integer such that when I multiply this n with this smaller number x, where x is a positive real number, I can make this product bigger than y. And this is exactly what we are going to discuss in the Archimedean property. Suppose my y is 1000 and my x is only 2. Now you can find a positive integer n that can make nx bigger than y. There exists at least one n exist. So suppose the first n that can make this product nx bigger than y is 501. So n into x, this is 501 into 2, that is 1002, which is exactly bigger than your y. There exists many n for which this product nx is greater than y. Now we will discuss its statement and proof properly. Let x and y are the two real numbers, where x is positive real number. Then there is a positive integer n such that this product nx is bigger than y. To prove this property, we will use contradiction. I will assume that this nx is not bigger than y. Then I will construct a set A that consists on the number of this form nx. Later I will show in the end that the supremum of the set A that consists on the elements of form nx is smaller than some element of the set itself. That leads to the contradiction. So we will prove the result by contradiction. Assume that the statement is not true, so that for some real number x and y, this product nx is always less than equal to y for all n belong to natural number. Next, I am constructing a set A which consists on the elements of the form nx, that is the elements on the right side of this inequality. This implies, as we have assumed that nx is less than or equal to y, this implies nx is less than or equal to y for all nx belong to A. This shows y is an upper bound of A. As A is non-empty, A is a subset of real number, and A has an upper bound in R, that is Y here, and R is complete. So by the completeness property of R, the supremum of A must exist in R. Suppose the supremum of A is alpha. If alpha is the supremum of A, then alpha minus x is not an upper bound of A, because x is a positive real number. As x is positive real number, so when you subtract this positive real number from alpha, alpha minus x will always less than alpha. Now the definition of supremum says, if alpha minus x is smaller than alpha, then it must be that there, if this is an element alpha minus x, and here element alpha, then it must be that there exists some element of set A. Suppose this is n naught x between these two elements. So there exists n naught x belong to A, where n naught is a natural number, such that alpha minus x is less than n naught x. Adding x on both sides, we have alpha less than n naught x plus x. Taking x as a common factor, we have n naught plus 1 into x. As n naught is a natural number, this implies n naught plus 1 is also a natural number. Let this sum n naught plus 1 is equal to n1. So we can write n naught plus 1x as alpha less than n1x. Next, but n1x is an element of the form of the elements of set A. This shows alpha is less than n1x, where n1x is an arbitrary element of set A. But it contradicts with the fact that alpha is a supremum of A. Hence, our assumption is wrong, because the definition of supremum says if alpha is a supremum of A, then it should be always greater than or equal to every element of A, set A. But here we have find some element n1x of A, for which alpha is less than that element. So this shows that alpha cannot be a supremum of A, hence our assumption is wrong, and hence nx is greater than y for xy belong to R, where x is positive real number and not n belong to n. And this completes the proof. So I hope now you have a clear understanding of Archimedean property. Inshallah, in the next lecture we will discuss a very important theorem, that is Q is dense in R. So see you in the next lecture. Take care. Allah Hafiz.